Hi, everyone. I'm Kwang-hee, a second-year master student working with Professor David and Shinji at CMU. Today, I'm going to talk about our paper, Leveraging Allophony in Self-Supervised Speech Models for Atypical Pronunciation Assessment. So as a background, I'll try to explain each keyword in our paper title, and our paper has two main themes: our method mixture P and its results, and the analysis on self-supervised features. So I'll go through both of them, and I'll end the talk with the takeaways. So let's look at our title again. There are three keywords: allophony, self-supervised speech models, and atypical pronunciation assessment. Let's go through those one by one. So to understand allophony, we need to first understand what phoneme is. So phoneme is a unit of sound that we produce. So in this case, how do we define the unit? The criteria is that it has to be meaningfully distinct. So for example, in the pat the cat, we distinguish pat and cat because p and k are different phonemes, right? Leading to different meaning. However, phoneme actually is not a singular thing because a phoneme can sound different depending on the surrounding phonetic environment. But many people actually don't realize this. For example, English phoneme t is not a single sound because when we compare the word tap with stop, like we put our hands in front of our mouth like this, tap compared to stop, you can feel significantly more breath in your palm. So butter and kitten are also good examples because for kitten, you don't even touch your tongue tip to your teeth actually. So that's what allophony is. So now let's see what self-supervised speech models are. So self-supervised settings are somewhat different to the usual supervised settings with input X and label Y because for self-supervision, you only have the input X, in our case speech, but no label Y to directly train the model. So we designed the self-supervised task by starting with input speech, and we mask part of the audio, and then we feed this masked audio to the learnable module where the transformers are often used. And finally, we train the module by forcing the model to reconstruct the original signal. So it's basically very similar to BERT and mass language modeling. So this approach is quite useful because there's abundant amount of data, but as always, labeling is expensive. So fine-tuning these kind of self-supervised speech models were a tremendous success for a bunch of downstream tasks like ASR, speaker identification, emotion recognition, you name it. So that's what self-supervised speech models are, basically foundation models for speech. So now let's see how we usually do a typical pronunciation assessment. For assessment, goodness of pronunciation, or GOP, is commonly used. And GOP is like the degree of similarity between produced and correct pronunciations of phonemes. So we use them for atypical speech, like such as pathological, like dysarthric or non-native speech, because like GOP shows which phonemes are mispronounced and to what extent each phoneme are mispronounced or atypical. For example, in this figure, low-scoring phonemes such as like t, like o, like are the ones are more pronounced atypical than others. So let's see how can we actually calculate these GOP scores. We start from speech that we want to assess, and we are assuming that we already know the ground truth phonemes and their start and end time within speech. Let's say we want to measure how well the person pronounced for the segment 2 in this case. So we feed that speech segment 2 through a phoneme classifier, which is trained with typical speech, and the resulting classification probability for 2 directly becomes the GOP score. So if the pronunciation was very atypical, then this score will be somewhat low, right? So in summary, we are solving the task of a typical pronunciation assessment, where we are calculating the level of atypicalness for each phoneme. So to do that, we need to model individual phonemes accurately, and that's where allophony comes in, we have to take allophony into account to model individual phonemes well. And actually, we found that such allophony information is well encoded inside the self-supervised speech models. So let's look at our method by starting with the limitations of existing GOP, because we use the fully connected layer for the classifier, right? And actually, this implies unimodality. In other words, a single cluster for a single phoneme. But as mentioned before, phoneme is not a single cluster, right? Also, a phoneme recognizer often uses softmax function, which assumes in distribution. However, the model is already trained with typical speech, but our input speech actually is atypical, in other words, out of distribution. So we solve this problem by using the mixture distributions rather than classification scores. We use the Gaussian mixture models to directly model the multiple clusters or allophones, and we also avoid using softmax scores by directly using the likelihood. So let's do a quick comparison between the GOP, the left one, and the mixed GOP, the right one. So input is the same, ground truth phonemes and their start and end time within speech. And we feed those speech segments through a model which is trained with typical speech. However, we swap the phoneme classifier with the Gaussian mixtures to have multiple clusters, so to model allophones. And we swap the phoneme posterior, the classification softmax score, with the phoneme likelihood to avoid the softmax function to model the out of distribution or atypical speech well. So in this case, our case, smaller the likelihood, more atypical the input to was, okay? So let's look at the results quickly. We use two classes of data sets, speech from pathological or dysarthric speech and speech from non-native speakers, a total of 5 data sets. We also use various types of speech features using traditional acoustic features or state-of-the-art methods and self-supervised speech features, a total of 5 features. And we compare 7 state-of-the-art methods. And yeah, like to summarize, we are actually one of the first to unify the pathological and non-native speech as framing as an out-of-distribution problem. Also, we implemented and conducted extensive variations of experiments, also newly releasing some of the text grids for the data sets. And our data set and the code base is quite easy to use, so you can check the code here. So let's look at the results. This is our method, the bold one. And our method achieves best performance across 4 out of 5 data sets. And actually, if we look closer to the results, in this case, the UA speech, we can notice something peculiar. The first row is from the traditional features, and the second row, self-supervised features. And if we look at the mixed GOP, the right row, we can observe the huge difference, huge performance gap between the two types of features, unlike the previous GOP methods. This often happens across different data sets also. So a natural question arises, why is mixed GOP so successful in self-supervised speech features rather than traditional features? So let's look at those self-supervised features more closely. As a motivating experiment, we observed the sound only, and it seems that self-supervised features are clustered in a very specific way, actually per their surrounding phonetic environments. For example, for the lower left cluster, is always after sh and before ns, so it's shens, right? So digging further, we wanted to actually concretely measure how much does these phonetic environments or allophony is encoded within the representations. So it turns out that self-supervised features, the blue and the orange lines, captures much more allophony better than traditional features. And also it turns out that the amount of allophony information correlates to actual downstream performance in pronunciation assessment in a positive way, up to a certain point where performance saturates. So let's finish with the takeaways. First, self-supervised features cluster per allophony. And Gaussian mixture seems to be effective in leveraging those allophony information for pronunciation assessment. And finally, we provide a unified way of understanding pronunciation assessment, framing as an out-of-distribution task and provides lots of resources for the benchmark. So thanks for listening and see you at the poster session.